Welcome back, physics fans. My name is Varun Yarabarla. This is my video report on Lab 3, the Black Hole Lab. The point of this lab was to quantify the motion of a star and use that information to determine the mass of the black hole, as well as analyze the relationships between various forces and the changes in momentum. The motion of the star was analyzed and modeled through VIDLE using a CSV file that was provided. Through the application of Newton's gravitational force principle and using the connections between the different FNet components and the change in momentum components, the mass of the black hole was determined to be 1.99 times 10 to the 31 kilograms. There are two main principles that are applicable to this lab: the momentum principle and Newton's law of universal gravitation. The momentum principle is in derivative form is dp dt equals Fnet. In words, the change of momentum, which is the effect, is equal to the net force acting on an object times the duration of the interaction, which is the cause. Newton's law of universal gravitation states that there is a force of attraction between all masses in the universe. The specific force of attraction is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, as seen in the equation. The constant g is approximately equal to 6.67 times 10 to the negative 11th. This is how the gravitational force equation will be used in the code and will be discussed later on in the video. We were given important information to come up with a model and code. Here in the code, we have the star's mass, the black hole's location, and the change in time, which were all provided for us. Here's the star data that was inputted into the code via the CSV file that was provided. The first while loop in this code is merely used to compute the velocity of the star during its trajectory around the black hole. Continuing on to the good stuff, we come upon the second while loop. So V final and V initial are defined here. From this, I'm able to find the momentum, P initial and P final, by multiplying the star's mass by its velocity. From this, I'm able to find delta V and delta P. dp dt is equal to the change in momentum over the change in time. According to the momentum principle, that is what Fnet is equal to. Then, I find the direction of momentum by using the equation of initial momentum over the magnitude of the initial momentum. From that, I can find the magnitude of dp dt parallel because it is the change in magnitude of the momentum over delta t. And I multiplied that by p hat in order to get the parallel component, which is the same as Fnet parallel. To find the perpendicular component, I do dp dt minus dp dt parallel because the parallel and perpendicular components sum together to make dp dt. And as before, the dp dt perpendicular is the same as Fnet perpendicular in terms of value because of the momentum principle. Now I'll go ahead and run the code. The star is orbiting the black hole, and these are the various components. The arrow was set to distinguish. The blue arrow was the perpendicular net force component, the black arrow was the parallel component, and the yellow arrow was the total net force. Using this one line of code that was shown earlier relating to Newton's law of universal gravitation, I was able to solve for the mass of the black hole. Essentially, the equation was rearranged solving for just the mass of object 2, which was the mass of the black hole. This is what the equation looks like when in Python code form. This portion is the magnitude of r squared. The denominator is essentially shown in the code by this. The rest of the values were known, so when the calculation goes through and the code is run, the mass is then printed in the shell window and has a value of 1.99 e to 31st kilograms. Now, let's answer the questions. Question 1. According to the momentum principle, these are all equal to each other. Fnet is equal to dp dt, Fnet parallel is equal to dp dt parallel, and Fnet perpendicular is equal to dp dt perpendicular. But they're different in the way that they're calculated. To find Fnet in this case, it is just the gravitational forces that can be found through the gravitational force equation shown here. To find dp dt, however, you have to derive it through another process by using change of velocities like I showed in the code, or using the equation shown here. The net force sometimes can just be found by adding up all the forces acting on the object, whereas dp dt is found by observing the motion of the object itself. Even though they're equal to each other according to the momentum principle, they are found in different ways, and that is why they are different. Question 2. What if? No, the mass of the black hole cannot be calculated. If the motion of the star is unchanged and the data points given in the CSV file are the same, then there is no alternative gravitational force to calculate a new mass of the black hole. If the motion being changed means similar path but different points, then you could calculate the new mass, but that is not the situation given here.